Hello. What I have here is a model built out of NEX of a 6-story buckling-restrained braced frame sitting on a shake table made entirely out of NEX. Right here, I can't really model the yielding component of buckling-restrained braces, so actually more like a friction brace, so it's not entirely accurate, but I'll show you what one of them looks like here up close. This is what it looks like, and it can slide back and forth and engages in friction. So it has a friction hysteresis curve. And then the little clips here at the end, it's kind of a little bit of a weak point. And so eventually the building will collapse because it has a failure point. And that's what you typically see with buckling-restrained braces. They have really good stable hysteresis, but if you extend them too far, they can break. So I've done analyses on buckling-restrained braced frames during my master's degree at Michigan Tech, and this pretty accurately shows the results from my numerical analysis, but with a NEX building instead. So I was really excited when I first ran it. Also, the beams here, or the representative beams, are these flexible rods here. And this is to kind of represent a pinned beam column connection, which is a typical sort of connection with buckling-restrained braces, buckling-restrained brace frames rather. Now you can have a moment frame boundary frame for the buckling-restrained braces, and that has a different effect. But with the pinned case, which is allowed by code, you can have large residual drifts. My research was in reducing the residual drifts of buckling-restrained brace frames, and the pinned condition is kind of the worst case condition. So let's see what happens when I use my power drill here to shake the building. So here we go. So as you can see, the bottom braces are going, and it's starting to get a little bit of permanent deformation maybe. Try to get the fundamental frequency here. Once it starts to get some permanent lean, then it'll start to engage in the direction more. So you start to get a little bit of P delta effects or second order effects. You go to it. Right there is about the fundamental frequency. Oh, there we go. So this is what progressive collapse through second order effects looks like. Like that. Pretty cool. Not what you want to have with your actual building, and but nevertheless is what happens when the building starts to lean too much. So the building starts to lean over, the weight of the building is multiplied by the displacement of the building, and that adds an additional moment onto the base of the building, which then causes it to lean in that direction more. Which is why typically with these sorts of buildings, you want to have some sort of elastic component to the boundary frame that can help bring it back to center. If you don't have any elastic component and it's all plastic or friction based, then you can have those permanent deformations. It's not what you want. So one thing you can do is you can have like a moment frame connection at the beam and column. Or you could have an elastic backup frame, which is what some people do. So they have like a rigid backup frame that's alongside of the more flexible and ductile buckling-restrained brace frame. So that's about all there is for this video. I hope you enjoyed the collapse simulation.